Okay, so this is a question about a diffuser. So hopefully you can read that, but I'll read it out anyway. So 6 kilograms of argon enters a diffuser with a temperature of 150 degrees and a pressure of 0.2 megapascals. It leaves the diffuser at a temperature of 200 degrees and a pressure of 0.22 megapascals. The inlet cross-sectional area is 0.01 meters squared. What is the outlet velocity? Alright, so for a question like this, we're going to want to draw a diagram. We should probably draw a diagram for every question. Okay, so a diffuser takes in fast air or fast substance and puts it out slowly. Okay, so it's a backwards nozzle. So I draw a diffuser like that. We have a mass flow a flow coming in and a flow going out. Okay, so we're told that the mass flow rate is 6 kilograms per second. We're told that it enters with a temperature of 150 degrees. Pressure of 0.2 megapascals, that is 200 kilopascals. I convert everything to kilopascals because my data tables are all in kilopascals. And it leaves at a temperature of 200 and 220 kilopascals. Okay, and we're also told that the area at the inlet is 0.01 meters squared. And it wants us to find the outlet velocity. So we can write our energy equation. So it's steady flow, so 0 equals the mass flow rate. And I'm going to write a long version of the equation for this question because it gets a bit confusing. So mass flow rate multiplied by h in, I'll just put that as h1, plus mass flow rate multiplied by a half v squared 1, so that's velocity in, minus mass flow rate h out minus the mass flow rate and the kinetic energy out. Okay, now you might have noticed there's a bit of an issue here. We have two unknowns in our equation. We don't know either velocity, but luckily there is a formula which we can use, which is that the velocity equals the specific volume multiplied by the mass flow rate over the area. Okay, so because it's argon, remember? The substance is argon. We can't use our data tables. We have to assume that this is an ideal gas. So we can use the formula PV equals RT to find the specific volume. So we can rearrange. So RT over P. And we can look up our, we still have to use the data tables for this bit. So we can look up our R value for argon. And I'm just looking it up now. It's 0.2081 multiplied by the temperature at the inlet is 150, but this has to be in Kelvin, remember? So we have to add 273 to our 150 degrees Celsius to get to Kelvin, so that's 423 over the pressure, which is 200. Now this gives us a specific volume of, just plug that in your calculator, and you get 0.4401. Now we return to this equation. 0.4401 multiplied by the mass flow rate 6 over the area 0.01, and this gives us velocity at the velocity 1 at the inlet, 0.4401 multiplied by 6 over 0.01. So that gives us a velocity of 264.06 meters per second. Now, we have V1. We can, okay, so we have to arrange the H's in a form where we can use our Cp delta T equals delta H equation. So if I were to add this to the other side and take that off, okay, so I have the mass flow rate of H2 minus mass flow rate H1. I'm going to subtract that as well, minus the mass flow rate, a half inlet velocity equals negative mass flow rate, half kinetic energy of the outlet velocity. Alright? Now, H2 minus H1 is delta H, so we can write this as mass flow rate delta H minus the mass flow rate, a half V squared inlet and the outlet kinetic energy. Alright, now let's write this. So let's put numbers in now. So the mass flow rate is 6. Now remember that delta H equals Cp delta T. So we have to look up our Cp value for argon. And the data tables tell me that it is 0.5203. Cp delta T. Now because this is a difference, it doesn't have to be in Kelvin, so the difference is 50 degrees. That's from our original drawing up here, or the original question. The data we got from the original question. Okay, so I'm just going to put this in brackets, and then minus the mass flow rate multiplied by a half times by the velocity at the inlet, which we found was 264.06, and that's equal to the kinetic energy at the outlet. Now, let's get our calculator out. Let's put this here. Can you see the numbers? No, you can there. Alright. 6 times 0.5203 times by 50. So you get 156.09. And now we do our kinetic energy. I'll just do it off screen, but 6 times a half times, oh hang on, this needs to be squared. Velocity squared, okay. 264.06 squared. Now, this is in joules. This equation is in kilojoules. So we got 209,183 joules, but we have to convert to kilojoules. So we move the decimal point to the left 3 times. So 209.183 kilojoules now equals negative mass flow rate half V squared outlet, the outlet velocity. Okay. Now get the calculator out again. We're nearly finished. 156.09 minus 209.183 is negative 53.093. I'm doing a lot of steps, but you can jump steps if you want. Alright, now the mass flow rate. Let's substitute 6 in, and we'll put a multiply sign there. Okay, so they're all multiplied. So we want to divide by negative 6 and a half to that side. So if I'll just do that on my calculator, minus 53.093 divided by negative 6 times a half gives us 17.697 equals the velocity squared at the outlet. Okay, so now we get down to this. Now this is in kilojoules, and I made a mistake up here. I told you to convert to kilojoules, but whereas we really want it in joules, but that doesn't matter. We can convert back to joules here. So we can say that it's 17,697 joules, because now we're dealing with the velocity from the kinetic energy equation. And then if we just take the square root of both sides, we find that the outlet velocity is 133.03 meters per second.